Hi there, thank you. So today I'm going to be giving the Genesis update, and I'm mindful of time, so I'll crack on. I guess I can't see everybody who's there, but I guess there might be some new people in the audience. But just to give you a flavor of what Genesis is, we're one of the threads within ASTRO 3D, and our focus is on studying galaxy formation and evolution across cosmic time from a theoretical point of view. So we do that using n-body simulations and SAMs, hydrodynamical simulations, n-body simulations, both non-cosmological and cosmological. We collaborate very closely with teams from across the world, for example, Eagle and Illustris. And we're also responsible for developing our own in-house software tools for generating and analyzing theoretical data sets and producing mock observables. So the lead CIs are Darren, Stu, and myself, and we have some postdocs, Kate, who's based here at ICRAR, although she will soon be moving on to join the Magpie team, which is very exciting, Yisheng and Manadeep. So over the next few slides, I'll give some research snapshots, some highlights of work that's going on around the various nodes, and I'm also mindful that we've got quite a few speakers presenting after this, so I won't steal their thunder. First, Yisheng over at University of Melbourne has been doing a lot of work on predicting the Lyman alpha emitters during the epoch of reionization, and he's been using Meraxes to make predictions for what the properties of these Lyman alpha emitters should be, both in terms of their intrinsic properties and also their clustering. So if you look on the left-hand side from your perspective, here's some recent work that Yisheng's done with Leonova et al. And what the plot is showing is the H160, the UV magnitude versus the number of nearby galaxies within a small patch of sky. And the 3 stars are indicative of the observation. So these are taken from some Campbell's EGS fields, and they compare very favorably with some theoretical predictions. So you can see what the clustering is like. If you look at, I'm not sure whether you can see my mouse cursor, but in the top inset just shows what the galaxies look like within that field. And the size, or these circles, are indicators of what the prediction should be from Meraxes run on a previous large n-body simulation called Tiamat. And so this shows how favorably how comparable the predictions are in relation to the observations. The lower inset basically just gives an indication of what some of these very bright galaxies will look like within the Tiamat simulation coupled to Meraxes. Yisheng has also been doing some nice work with the large Genesis simulations that we've been running, and he's got an indication of what the UV magnitude should look like versus the equivalent width that we measure. And so this is telling us something about the star formation properties of those galaxies that are helping to drive reionization. Yisheng's also been doing some additional work looking at the impact of stochasticity on the epoch of reionization. So what do I mean by that? When you look at what's driving the epoch of reionization, it's the UV flux from hundreds upon hundreds of galaxies, and these will actually dictate what the morphology that we observe within the IGM is, and on the scale it's probed by 21 centimeter emission. Sorry. And this stochasticity can arise in various ways. So for example, it can come from the occupation of galaxies within their dark matter halos. So if we look at the stellar mass halo mass relation, or it can actually come from the intrinsic UV ionizing luminosities from the individual galaxies. So if you look on the left-hand side, this just indicates what the stellar mass halo mass relationship looks like at redshift of 5. This is taken from work by Simon Much, who was one of our Genesis PDRAs at an earlier point. And it shows what the stellar mass is versus the halo mass at different redshifts, and you can see how consistent they are. So that's what's being shown in the bottom of the bottom panel. On the right-hand side, these are projected density plots, so showing the neutral hydrogen fraction within one of these co-moving volumes. On the left, this shows what the stochastic prescription looks like. On the right, it shows what the constant prescription looks like. And in this case, there's no stochasticity in there at all. The top panel show what it looks like at redshift of 8. The bottom panel shows what it looks like at a redshift of 6. And the difference map shows what how comparable they are, whether or not this stochasticity is included. And so this is actually that's work that's continuing. So Yusheng's been working with Balu on using Meraxes to study this, and they've been working with the enhanced Genesis boxes. So they're the boxes that Balu's been working on by extending the clustering of galaxies or the clustering of halos below the resolution limit of the simulation using some techniques that have been developed at the Melbourne node over the last few years. Moving on to work that's been done by Darren and Manadeep. So they've been involved in these big Uchu simulations that have been run in Japan by Ishiyama and collaborators. I guess really what you can take away from this are some very gratuitous pretty pics showing the large scale structure. And what's nice is that as you zoom in to smaller and smaller scales, you can see that you're not losing any, and you're not really losing very much in terms of the resolution. And the particle mass here ranges between a few times 10 to the 8 and just below 10 to the 6 solar masses. So as you'd expect from these kinds of runs, you can derive merger trees. And so work that's been done by Dylan over at Swinburne as well has very much focused on using these merger trees to predict how and when massive quiescent galaxies form using these simulations, and then coupling them to the SAGE semi-analytical model. And so on the left-hand side, this just gives an indication of what the merger tree looks like, what the mass accretion history of that halo looks like. And then Dylan has used this to infer what the properties of the stellar mass within these massive quiescent galaxies look like over redshift. And that's what's been shown on the right-hand side. And so Dylan will be working with Carl, who's also Carl Glazebrook, who's also one of his supervisors, to compare the results from this modeling with JWST once these data start coming in. Moving to the EWA node, the ICRA EWA node. So Adam Stevens has been working very, very hard on his new semi-analytical model called Dark Sage. And the key feature of this is that it's the first semi-analytical model of galaxy formation with multi-dimensional disk structure. And so what that means is that you can fully reconstruct the histories of galaxies on a per component basis. So it takes into account the angular momentum structure of the infalling gas to construct the disk, and therefore you can have resolved star formation within annuli within these disks. Some predictions from Dark Sage. It's quite a busy plot, but this is showing the star formation density versus look back time on the top panel in different mass bins, so 10 to the 9 to up to 10 to the 10, all the way through to massive galaxy greater than 10 to the 11. And the lower shows the mean metallicity of the star forming material within the model. Adam's also provided some additional plots. So this is just looking at the galaxy occupancy within as a function of the stellar mass, or the number of galaxies as a function of the stellar mass, the co-moving number density of galaxies as a function of stellar mass. This shows the, well, that's basically the stellar luminosity function. Sorry, brain fog. This shows the plot here on the right-hand side shows the H1 luminosity function. This is showing what the star formation rate density looks like as a function of redshift. And so these are some nice predictions coming from the model. And one of the key selling points as far as Adam's concerned is that there are only 2 free parameters that need to be calibrated in order to recover these predictions. The first is just the radiative efficiency of black holes, so that's controlling the black hole feedback. And then another one that controls the movement of mass instabilities when the disk becomes more unstable. Coming on to some other work that's been done here at ICRA EWA. So this is some recent work by Katie, or well, it's a little bit, it's not her most recent work, but it's still very interesting. So Katie's been working on the formation of intrahalo light. And so the idea is she wants to decompose the stellar component around galaxies and see how that encodes information about the assembly history of the galaxies. And so this is, it's quite a difficult thing to do both observationally and in simulations, but Katie wanted to devise a method that would allow her to define the IHL in both observations and in the simulations. And so she's been doing this by, at least in the initial stages, by building galaxy models and then using machine learning to decompose the systems into their various components, i.e. the halo, the bulge, and the disk. And so the key thing on the right-hand side shows the specific binding energy versus the angular momentum of the material. And so you can see that this does a pretty good job of separating out the disk from the disk from the bulge from the IHL. And so applying this to some theoretical data, a realization of a galaxy, and comparing to other prescriptions, it seems to perform very, very well. So that's what's been shown down on the left-hand side. This is showing the enclosed stellar mass as a function of radius. So Kate Harborn and another member of the team here over at ICRA EWA, who, as I said, will be moving on to join the MAGPIE team shortly, should be well known to many of you. So she has been the driving force behind SimSpin, which is this theoretical tool, or it's a tool for taking theoretical data sets from numerical simulations and then turning them into integral IFU data sets, data cubes that can be compared with the likes of Sami and Hector and Manga, et cetera, et cetera. And so Kate sees herself sitting very much at the interface between theoreticians and observers. And so Kate's been doing some interesting work recently in support of the next version of SimSpin to generate data products that can mimic the velocity resolution of a given telescope and produce output similar to the IFS kinematic maps.
Sorry, Chris, you have 2 minutes left.
Okay, yeah, I should be done then. Thank you. And so this schematic up here just gives an indication of what that pipeline is doing. So going from something that looks like that all the way through to something that can be put into, well, whatever the observers use to measure their IFS data cubes. And also doing it in spectral mode, so producing data products that can fully recreate the observed spectra that can be run through the observed pipelines in an identical format to observations. The outputs of these two methods are very similar, and so Kate's been using SimSpin to do some very nice work. So looking at comparing the galaxy kinematics from different simulations with different resolutions to make mock observations useful for training machine learning algorithms and to investigate the effects of simulation subgrid physics on the kinematic structure of individual galaxies. And I think Caro would have shown some of the work that Kate's been doing yesterday for the theory data release from MAGPIE. So that shows the power of this tool and all the work that Kate's been doing. Just something else to add, Kate's been working with ADAX team, so she was successful in getting some ADAX time to support taking SimSpin to the world, I guess. So developing an API that will allow SimSpin to be run as a web app, and so it'll be able to deliver these data wherever you are in the world. Okay, so that was a pretty quick run through work that's being done at the various nodes by various Genesis team members, and you'll hear more from the Genesis team afterwards. But we're pretty much engaged in like it's ongoing work. So the n-body simulations coupled to both the semi-analytical schemes, semi-empirical models. I didn't really mention much of that, but Manadeep's been doing some nice work in that area. They're ongoing. We're running our own in-house hydro sims. That's mainly me, I guess, looking at inflows, outflows, mixing turbulence, trying to understand what are model specific predictions, which are model invariant, So on the right-hand side, there's just an example of some work I've been doing recently, trying to understand running the same set of initial conditions with the repo, gadget, and Swift, with star formation and feedback, and trying to distinguish between them, looking at where the differences are. We also have team members who are working very closely with the big teams, and there's lots of excitement around Calibri, which is the successor to Eagle. So Claudia and Aaron are probably the go-to people for that. And I guess it feels sometimes like we're the incredible shrinking team because we are quite person power limited. We're seeing lots of students graduate and doing well, which is really good. But it does mean that we're a bit tight for people sometimes. But nevertheless, I think we're very happy to work with the teams on projects that are mutually beneficial and trying to figure out ways in which we can work with you. And okay, that's it. Thank you.
Thank you, Chris.